Alright, gang, welcome back. GPH 111. The experience continues. Last time we talked about plate tectonics. Today we're talking about volcanoes and earthquakes. So here's our game plan. We're going to talk about types of volcanic eruptions and the importance of viscosity, how rock class impacts landform type. Then we'll talk about dangers associated with volcanic eruptions, also a little bit of positives. Then we'll talk about how earthquakes work and earthquake dangers. So you guys all know what volcanoes are. That's when magma erupts onto Earth's surface. Magma is that hot lava looking stuff that looks really cool. And those National Geographic videos of Hawaii, red stuff spewing onto the surface. The reason volcanoes erupt on our surface is because the inside of our planet is hot. It's hot because of the decay of unstable elements inside our planet called isotopes. These isotopes, as they break down over time, they release energy that generates a bunch of heat, and as that heat works its way from the core of the planet to the surface of the planet, we get these convective currents that drive plate tectonics. And as these plates move over the surface of the Earth, as our ocean floors rise up to the surface, then sink back down, rise up to the surface, sink back down, as our continents, the pot scum moving over the surface of the planet, all this leads to molten rock erupted onto Earth's surface. The reason that liquid rock will erupt onto the surface is because it's less dense than the hard rock that surrounds it, so it gets shot onto the surface. There's at least 1,500 active volcanoes on the planet. Most of these are along the Pacific Rim of Fire. That's where the Pacific Ocean is getting eaten up. The Pacific Plate is getting eaten up over time on all sides. The Andes of South America, western coast of North America along the Seattle, the Aleutian Trench of Alaska, all the way over into the Kamchatka Peninsula of Russia, down along Japan, all the way down into Indonesia. It's getting eaten up on all sides. There's roughly 50 to 70 volcanic eruptions every year, and they're powered by isotopic decay, or radioactive decay. I call it isotopic decay because it's the isotopes that break down over time. In this image here, we have Mount Pinatubo, 1990. This was the largest eruption of the last century. It was in the Philippines. Absolutely massive eruption, and what's fascinating about it is that it was the first eruption predicted by geologists. They knew it was going to happen, they called the evacuation, and it was a huge success. Okay, so I would take notes on this I would take notes on this if I were you. So we have three, roughly speaking, types of volcanic rock. We have basalt, andesite, rhyodacite. Roughly speaking, the three different types of rocks are associated with their silica content. So for basalt, we have a silica content of 48 to 55%. Andesite, we're as high as 55 to 60%. And finally, rhyodacite, we're up to 60 and 77%. So who cares? Okay, first off, silica think of it like sand. Sand is actually quartz, which is silica and oxygen. But silica, it's a light element, mineral. And as you go from basalt's actually very dark. Then as you move into andesite, you get kind of purplish in color. And then finally, rhyodacite, it's actually very, very light in color. Okay, more silica, lighter in color. Also, as you get more silica, you increase viscosity. So what the heck is viscosity? Viscosity is the resistance to flow of a liquid. Okay, the higher the viscosity, the higher the resistance to flow. So honey has a high viscosity. It has a high resistance to flow. Whereas water has a low viscosity, right? It flows very, very easily. Basalt has a low viscosity. Rhyodacite has a high viscosity. This activity time thing that I have down here, I'm going to actually do this with you guys in lab so you can see it. And what you're going to find out when you do that activity is basalt is low silica, low viscosity. It's going to be like soda, like Pepsi or Coke, and it generates mild eruptions and it flows fast. Andesite is medium silica, higher viscosity. It's going to be like syrup, like you would put on pancakes, and they're violent to explosive eruptions. Once we get up here to rhyodacite, we have high silica, very sticky, high viscosity. It's going to be like honey. Because it's so sticky, it might actually be a mild eruption because the gases never erupt, but it also can generate the most explosive eruptions on the planet. In a gist, the idea is you have dissolved gases in the magma, okay, in the lava, in all of these. And as that lava comes to the surface, just like in soda pop, when you open soda, the gases basically come out of solution in the soda, become bubbles, okay, because you've released the pressure that was put in it when they made the soda. Lava, when it reaches the surface, it gets a huge pressure release and all these bubbles pop out of solution, okay, and they want to rise to the top because they're very light. In basalt, no big deal. These bubbles rise to the top and you generate these flowery, beautiful eruptions. Andesite, however, as these gases pop out of solution and rise to the top, because it's so sticky, the eruptions can actually be very explosive as these gases try and get out. And rhyodacite, it's extremely sticky, and the gases have a really hard time getting out. So when they do get out, boom, you generate a massive eruption. Okay, so now we're going to take a look at different landforms associated with volcanoes. And what they look like is more or less determined by what kind of rock makes them. So we're going to take a look at cinder cones and shield volcanoes, which are both basaltic. Composite volcanoes, which are andesite up to dacite, moderate to highly explosive composite volcanoes. Lava domes, these are that kind of quiet, non-explosive eruptions, but it's very high silica dacite to rhyolite, but the gases never get out. Then we have calderas, where you can have andesite to rhyolite, and they can be extremely violent and explosive as those gases get out. So here's our cinder cones. This is Hawaii. Look at that beautiful shower. The reason it's all bubbly is these are the gases trying to get out. It's like brrr, 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 as the gases are getting out of this lava. But because it has low viscosity, low silica, dark in color, those gases have an easy time getting out. So it just makes this pretty shower. Once the gases get out, it just flows over the surface in this nice, really pretty ooze that I would love to, at some point, take a magical metal spoon and collect some of this stuff. Because then you get a brand new rock, a rock that's like 1 minute old. Everybody wants that. This is SP Crater, Northern Arizona. Excuse my language. SP stands for Shit Pot Crater. And you can kind of see how it has that name. It's a beautiful cinder cone. This is the lava spewing out from it. So the reason you have these cinders around it is because it's from the showers, right? Those showers, as they shoot up, the cinders fall down in a circle around the vent. But then again, once you have the gases out of it, the lava just flows out over the surface. And it makes a very beautiful landform. All right, shield volcanoes. Shield volcanoes do not look very dramatic. They're huge, really gradual domes, but they're massive. This is Mauna Loa, the big island of Hawaii, and it's huge. It's very shallow, but it goes up to 13,500 feet tall, all the way from the bottom of the Pacific Ocean. Here's Mount Rainier to scale. Okay, it's an absolutely huge feature. A tremendous amount of lava gets erupted. The reason the feature is so shallow is because the magma has low viscosity. It's very easy to flow. It'll flow on very gradual terrain, and so it builds a very gradual terrain feature. This is an image of Olympus Mons. Olympus Mons is on Mars, and it's the largest mountain in the solar system. It's 80,000 feet tall. 80,000 feet tall. Boom. And the area of the volcano, again, because it's also very shallow along its size, is the size of Arizona. You're going to form shield volcanoes because basically take a cinder cone, that same process, and run it over a long period of time, you're going to build a shield volcano. All right, composite volcanoes. When you think of composite volcanoes, you're thinking of the classics, right? Mount Fuji. Who doesn't think that mountain is beautiful? Okay. When we're getting up here to composite volcanoes, the features are getting steeper. And the reason why these mountains, these landforms are steeper is because the viscosity is higher. It takes a steeper gradient, a steeper slope in order for that lava to flow. When you have an eruption, the lava comes up, and again, you pop the cork, and boom, all the gases get out, and it's massively explosive. So it rains ash all along the side. Ash is basically pulverized rock that blankets the mountain. But again, once you get the gases out of it, then you'll have lava that flows over the side. The reason they're called composite volcanoes is first you get that ash layer from the initial eruption, then once the gases are out, the lava will flow over the top, and so you get these layers. Okay, those layers is where it gets the name a composite volcano. We're out of basalt at this range. We're into the andesite range of volcanic rocks because our silica content has increased, therefore viscosity has increased, therefore we're getting more explosive. Here's some images of Mount St. Helens, the most famous stratovolcano. Oh, I apologize. I called it a stratovolcano. Stratovolcano is identical to a composite volcano. They're two names, and I use them synonymously. I apologize about that. Mount St. Helens is a very famous composite volcano. Here's an image of it before the eruption, and here's what it looked like right after in 1980. Okay, what's famous about Mount St. Helens, and here's what it looks like in eruption, is you can see that it didn't blow straight up. It actually blew out to the side. That's what made it very, very dangerous and very explosive. Here's a series of side images. So as the magma was coming up in Mount St. Helens, it found a weakness and it pushed off to the side of the mountain and it started forming this huge bowl that was growing daily. It was being measured. Okay. Eventually, the weight of the mountain got so heavy because of that extra magma, it collapsed in a huge landslide, one of the largest landslides in recorded history. And then you can imagine you basically, boom, pop the cork on this entire volcano, all the gases rush out, and you generate a massive eruption. But it's an eruption with a direction. It blew to the north, and therefore a lot of people died because they thought they were safe, and they would have been if it blew up. But because it blew to the north, if you were north of it, it was very, very dangerous. Here's some images. You definitely would want to not be at these locations. Or in this Jeep. This is a pyroclastic flow. We'll talk about it in a minute. You don't want this going over your vehicle. You drive very, very fast. This is Mount Pinatubo, the eruption kind of after it went off. This is like it's after the big eruption, it had a little coughs. This is one of the coughs. This is what it looked like from a distance. This is what it looked like from an Air Force base in the Philippines next to Mount Pinatubo. And they evacuated this Air Force base, and it was subsequently destroyed by ash that collapsed all the buildings. Here's a really pretty composite volcano out along the Marianas Trench. Marianas Trench is where you have a convergent plate boundary between two oceanic plates. The heavier one is diving underneath. It forms the deepest ocean on our planet. But you also get partial melting of that ocean floor. What melts comes up to the surface and forms, in this case, a very beautiful volcano and a beautiful eruption. All right, lava domes. A lot of composite volcanoes, after the eruption, they'll get plugged up. Basically, the sticky, gooey rhyodacite rock that's in the magma chamber comes up and it plugs up the magma chamber. And it's like, like a big blobby thing. Okay, and it doesn't explode because gases never escape from the magma itself, so it doesn't explode. Here's Mount Eldon in northern Arizona. Here's some lava flows coming off this lava dome. You can see this is very steep and it doesn't flow very far. It's like toothpaste. It just kind of comes up and onto the landscape. Blue is technical for how these things operate or not. All right, now it's time for the main event, calderas. Calderas are the big bad boys. Usually there isn't actually very much left of the volcano after a caldera erupts. That's because the magma chamber empties. And you end up with this huge cavern underneath the surface of the Earth. That's not stable, and so the Earth will collapse into that hole. So after these massive eruptions, you end up with famous holes in the ground. This is the Long Valley caldera in California. It's one of the biggest, most dangerous volcanoes on the planet. 760,000 years ago, it released 160 cubic miles of rock. Boom. 15 miles wide. That's how big the hole was. This is Crater Lake. I apologize, I don't actually have that movie. This is actually pretty stupid anyway. Crater Lake in Oregon. This was an andesite feature, but it was so explosive that it collapsed in on itself and formed a beautiful caldera that filled in with fresh water. And now the mountain is in the process of rebuilding itself. Here's Wizard Island right there, which is it's just so cool looking. This is Yellowstone caldera right here. This is the most dangerous volcano on the planet today. It's called a supervolcano. 600,000 years ago, it erupted 71 cubic miles of rock. It's currently in the process of rising. A dome feature is forming on it as the magma chamber underneath is building up. No indication that it's going to erupt, but if it does, it's huge. And again, you don't think of this like a volcano, right? Because it's just this area on the surface there that actually looks flat. Again, that's because this was a huge hole, and now the land is rebounding back up over time. All right, some dangers associated with eruptions. First thing you can get is a lahar. A lahar is when you get an eruption, you can often have snow or glaciers on the side of the mountain. Well, when the hot lava touches those glaciers or snow, it melts rapidly and get these huge mud flows pouring off the side. These are trees that took out this bridge during the 1980 eruption. These are very, very devastating. You don't want to be around when these things happen. Pyroclastic flow. Pyroclastic flow this is the ash cloud. Once it erupts up into the air, the heavier particles fall back down. But as they fall back down, they're going to travel down along the flank of the mountain like this. This is Mount Paley in 1902, the first time it was ever observed and recorded. The pyroclastic flow will flow down the flank of the mountain. They can travel over 400 miles per hour, and the gases and rock fragments in this thing can have temperatures over 2,000 degrees Fahrenheit. Here's some cool videos that I'll put on the Canvas page for you guys to check out. You don't want to go in these. This is what keeps volcanologists up at night, because you burn to death, you burn up your lungs inside these things. No bueno. Another issue, I just covered 3 issues. Obviously, if you fall into lava, that's bad, that's a danger. Don't do that. I didn't cover that as its own thing. CO2 emissions, gases that get emitted from the magma chamber below come up onto the surface. So in this area, actually, I grew up camping at this lake. The CO2 has come onto the surface, and it's basically poisoned these trees and killed these trees. And if you read the sign, what it says is, don't take a nap in a low spot, because CO2 is a heavy gas and it'll fill in the depression and you won't have oxygen to breathe. There was a famous event in Cameroon, Lake Nyos, in 1986, where a bunch of CO2 was basically getting dissolved in the bottom of the lake, and then eventually that bottom of the lake got lighter than the top and it flipped over. When that water came to the top of the lake, it was no longer under pressure, and all the CO2 basically bubbled out of solution. And because it's heavier than normal air, it flowed out of this lake down into a village and killed 10,000 people. And it was really creepy, because when people came into the village, there was no indication of what killed them. Everyone was in their beds, and anyway, freaky stuff. This is Mammoth, California. You can also have sulfur dioxide. Sulfur dioxide is poisonous, 13,000 tons released every day, but you can smell it, so you tend to avoid it. Okay, so take a minute and think about what are some positives associated with volcanic eruptions. What are some positive things? I'm going to take a sip of my drink. You keep thinking. First one we got is fertile soils. Fertile soils. This is Easter Island out in the middle of the Pacific Ocean. And what's fascinating is the ash from volcanoes, when it falls onto the ground, it makes the ground very, very fertile. So it's like rock candy for plants because it has all the nutrients and stuff in it. No other plants have taken it. They think Easter Island, the reason why this area is totally devoid of trees and life is when the Pacific Islanders traveled to this island, they were used to very, very rich soils that were constantly getting ash rained on them. But because this is in the middle of the Pacific where there are no volcanic eruptions, they cut down all the trees, the thin soil that was there washed away, and they basically collapsed their civilization. Really sad. But on a positive note, fertile soils come from volcanic eruptions, the ash, rock candy. Geothermal energy. This is in Iceland. Iceland is along the Mid-Atlantic Ridge, and it gets 90% of its electricity by basically pumping water down near magma chambers where it gets really hot and allow that water to turn to steam and turn generators and generate electricity. Really, really cool. We actually have one of these plants. If you drive on the 8 freeway towards San Diego, just outside of El Centro, there's a geothermal plant. And you also get new land, obviously not quickly. And here's actually a pyroclastic flow into the ocean. Don't live there, that's bad, dangerous, whatnot. But you get new land as associated with volcanism. And everybody appreciates new land. All right, here, take a minute and think about this. If you knew this was going to happen, this is in Hawaii. Here's a basalt flow that's flowing into a village. All right? As it flows in, beautiful rainbow in the background and a lava flow. Bummer. If you're living in this village, there's no reason to stay, right? You lose. Lava wins. Lava will destroy your town. There's no ifs, ands, or buts. But oftentimes when you have pyroclastic flows and that can travel 400 miles an hour, you're not going to have time. You have to basically be away before the eruption occurs. So the question is, how sure do you need to be the eruption should occur before you evacuate? So take a minute. Do you need to be 10% sure the volcano will erupt? 90% sure it will erupt? Take a minute and think about it. If you have a hard time coming up with an answer, that's because it's tough. You don't want to basically be too low, 10 or 15%, because if you have everybody evacuate, that's very expensive. They have to leave their jobs, leave their house, deal with their pets. And then if it doesn't erupt, you basically cried wolf and no one will believe you in the future. But if you wait to 95 or 99%, while you're waiting to see if it's going to erupt, it erupts and then you have massive casualties. So it's a very, very difficult job to determine when to call an evacuation or not. Not a job I want. Okay, so let's talk about earthquakes. Earthquakes are detected by seismographs. I'll have a movie, it's kind of a clip really, that shows you how seismographs work on the Canvas webpage. It's rated based on the Richter scale, so you hear that all the time. You get an eruption, boom, there was a 7.0 earthquake or a 6.0 earthquake. The trick is, though, is that the difference in energy between a 3 and a 2, or a 4 and a 5, or a 6 and a 7 is 31.5 times more energy between each level. So it's a little bit misleading. So like a 6 and a 7 might sound similar, but in reality, there's vastly different amounts of energy being released. You can also have the modified Mercalli scale. This is based on the amount of damage that occurs. And obviously, big earthquakes happen very rarely. Small earthquakes, much more common. The trick with gauging how dangerous an earthquake could be is you could have, like, say, a 5.0 earthquake, and everybody feels it, and there's slight damage to buildings. But that could be slight damage to buildings here in the U.S. that are built really well. But if you're in a third world country that things are not built well and they're not built on very good soil, that can turn to liquid, shake rapidly versus nearby rock that doesn't shake, it can actually be very, very destructive. Elastic rebound theory, I'll talk about in a second, and then we'll talk about evidence and damage from an earthquake. Don't look at that. So here is a strike slip fault. Energy is pushing this way and energy is pushing this way, and Here's kind of a line. As that energy builds up, you get this flexure on the landscape. You can actually have fences that bend right along the fault. Right? It's building up, it's building up, it's building up, and then eventually, boom, it's going to break. And it literally causes the break right there. You can think of it like, as this is building up, it's like pulling a bungee cord. The bungee cord is getting pulled, till eventually the frictional resistance holding these blocks in places are not enough to basically keep them together, and boom, it'll break, and it'll break rapidly. The epicenter is a location of maximum movement on the surface. The focus is the location of actual maximum movement, which is always in the subsurface. Okay? The energy builds up over time, like pulling on a bungee cord, till eventually the frictional resistance between the two blocks isn't enough, and bam, they snap. And they'll break and go back into equilibrium. And then the energy will build up again, and it'll push, and the same thing will happen. This was a while ago, 1989. Actually, it's kind of embarrassing how long ago. It doesn't seem that long ago to me. This is the World Series earthquake in San Francisco. Here's the focus. Here's the epicenter. It's along the San Andreas Fault. San Francisco and Oakland are up here fairly far away, but it's a sizable earthquake. The Bay Bridge busts. This piece breaks off. That looks really bad, but the bridge is actually designed to do that. It's designed to break there and not actually a much worse place to break. The terrible thing, though, is that this double-decker bridge collapsed. So the bridge up here fell onto the bridge below, which obviously cars are down here and they got smashed, which is absolutely terrifying. And there's a famous story where a guy's driving a truck, and he's driving underneath this freeway, and the earthquake's going on. And in a car, it's kind of hard to tell if an earthquake's occurring. Your car's just not really behaving, but it has shocks and absorb it. But he looked in his rearview mirror, and he could see the bridge falling behind him. Boom, 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 boom. And if I was in his position, I likely would have stepped on the gas and said, I'm out of here. He did the opposite. He hit the brakes and stopped. And he happened to stop on the only section of that double-decker bridge that did not fall down. And after he stopped, he saw the rest of the bridge, boom, 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 fall in front of him. Absolutely crazy. There's two pieces of field evidence associated with earthquakes. The first one's fault scarps. Fault scarps are awesome. This is the actual break of the fault itself. Like I had talked about before, the energy builds up, right? That frictional resistance between the two builds up, and then eventually, boom, it'll break. This right here is the break of the fault itself. This is a massive fault scarp from a single earthquake in the early 1900s in California. Here's one in Taiwan. You can imagine this is a bummer. You have a track that now has a hill in it. The tracks aren't supposed to have hills. That's going to be tough to deal with. This bridge didn't make it through an earthquake, but considering that this is a fault scarp, this river is now pouring over the fault scarp, basically like a river pouring over this thing. This waterfall is brand new. This actually held on pretty good. They're step-like linear landform, coincident with a fault trace. Fissures. These are huge cracks in the ground that can form as you rent the Earth's surface, but there's no offset. Okay, like here, this land was up here, and then it went boom. It fell down suddenly. Here, there's no offset of the fault, but it just cracks open, just boom, breaks open. Not that you want to fall into that thing. Damage associated with earthquake. There's a famous Japanese saying, earthquakes don't kill people, buildings do. The idea behind that is if you're out in an open field and there's a massive earthquake, you're just going to bounce around on the ground and, ride it out. As long as you're not near any mountains or hills or rocks can fall on you. But, I mean, look at these buildings. It's just absolute insanity. Here's a sagging freeway bridge. It's the buildings that are going to be an issue. All right, guys, so here's your things to know. Basic volcanic rock breakdown based on silica and viscosity. Basic associated with volcanic forms. Tied rock types, cinder cones, shields, composite cones, lava domes, calderas. You need to know that low viscosity eruptions tend to be much less violent than high viscosity. We talked about dangers associated with volcanisms, positives associated with volcanism, problems with volcanic, and the same is true for earthquake prediction. How earthquakes are generated with the elastic rebound theory, and then field evidence associated with earthquakes. Thanks so much, guys. Hope you have a great day.